Hi, and welcome back to another calculus video. Today we're going to talk about antiderivatives. And so what you need to understand about antiderivatives is that it's a British English word. And so when we talk about anti, in the American English language, anti means we're against things, right? It means we don't like things. An antiderivative, in the truest sense of the word, means the opposite of a derivative. So we're going backwards. In the British English, we talk about clockwise versus anti-clockwise. In American English, we say counterclockwise. Well, anti means the opposite when we're talking that British English. And who developed calculus but Europeans? And what type of English do Europeans speak? They speak the King's English, right? So British English. So antiderivative really just means we're going to take a derivative and go backwards and figure out what function did it come from. So when I identify some functions that could have the derivatives of these four things that are listed here, what I want to do is I want to think about, well, where did it come from, right? So what could be the original function for number one? Well, we're going to remember that when we take a derivative, when we have an exponent, that exponent gets brought down and multiplied. So whatever exponent I have here, it had to be one higher, right? So this exponent of 1 had to come from an exponent of 2. Now, whatever that exponent is in the original function then gets brought down and it's multiplied, right? So it's multiplied by 2 and then we reduced it by 1 to get to the 2x. So I have to think about, well, was there anything in front of the x that multiplied with that exponent of 2? And here the answer is no. So this f prime of 2x could have come from f of x equals x squared. This is one possibility. So let's take a look at number 2. And maybe you can pause the video if you're kind of getting the hang of this and you want to try it out. You go right ahead, pause the video, see if you can come up with these functions. But I'm going to keep on moving. And when I try to figure out in number 2, what function does this possibly come from? Well, I'm going to remember that when I have a constant in a derivative, it always started out as having an x with it, right? So if I say 5x, the derivative of 5x is 5. So if I'm getting a constant as my derivative, it started out with an x. And it started out with an x to the 1 power. Number 3 has a cosine. Hopefully you're kind of remembering that when we have cosines, cosines always come from sines. So the original function here was probably a sine. And then here in number 4, this one is the tricky one. In number 4, this function had to come from something with some bigger exponents. So this x cubed, it had to come from an x to the 4th power, right? Because the exponent's one higher. But remember, to get this derivative, it turned into 4x cubed. So there's no 4 here in that term. So whatever I multiplied by, there had to be something there to make it go away. And the only way to make it go away was to divide by that 4. Now if I do that derivative and bring the 4 to the front, it'll cancel away and give me just x cubed. So then this 4x had to start out as a 4x squared. And I'm going to remember that this 2 had to multiply with whatever was in front. Well, if there's nothing else with it, it gives me an 8x. That's not what I have. So I need to cut that in half to be able to get it down to a 4. So I'm going to divide by 2, okay? So this had to come from 4x squared divided by 2. And if I simplify it a little bit further, we can just leave it as 2x squared. And then this minus 1 probably came from a minus x. Now my question for you is, if these are all the original functions, are there other functions that these could have come from? Can you think of other things? Like, for example, what if number 1 wasn't just x squared? What if it was like x squared plus 7? Would that also give me a derivative of 2x? Are we remembering that constants, when we do the derivative, they'd go to 0? What if I had 5x plus 1? Would that also match? And by that token, what if I did any other number? Would it matter what number I picked? And if so, and if not, doesn't that lead me to understand that there's an infinite number of possibilities, because I could pick any number from negative infinity to positive infinity to be my constant? This is an interesting conundrum, because when we start with a derivative, if there's ever a constant in the original function, unless we're given some information about the original function, there's no way to know what that constant was. We need some sort of initial condition. And so that brings us to our definition of an antiderivative and some terminology and technical way that we're going to write some things here. So the true definition of an antiderivative, and notice this is not a typo, the antiderivative uses this notation capital F of x, which is super duper confusing because I mean, how else are you going to denote that if we're starting with a function f? Well, then how do we denote that we're finding an antiderivative, right? So we use the capital letter F. And so capital F is an antiderivative of a function f. Notice this one doesn't say f prime, it's just saying any function. If capital F prime, so the derivative of the antiderivative gives you the function in question, gives you f of x. So what you need to understand is that this phrase antiderivative, you don't have to be using an f of a capital F. So like, for example, if I start with, we'll give ourselves just a little bit of space up here. If I have capital F and then f and then f prime and even a second derivative in there, what I want you to be comfortable with is understanding that f of x is an antiderivative of f prime. F prime would be an antiderivative of f double prime, okay? So you're not stuck with calling it capital F. It's just a notation. So if I say a function f of x has an antiderivative, if it's not already f prime, well then we needed something to go back from f of x from. So that's when we use that capital F. So just understand that an antiderivative essentially takes any function and brings it backwards. It considers the original function to be a derivative, and it's finding the function where that derivative could have come from. So don't let the notation get you down. And furthermore, it says this: if f prime is 0, then there's a constant c for which f of x equals c. So if we know an initial condition, oftentimes there's some constant that we need to consider. Now, if we don't have an initial condition, what we do is we acknowledge the constant. And so down here it says this: if f prime equals g prime at each interval, then there's a constant c such that f of x equals g of x plus c. This is essentially saying that if we go back up here to all these problems that we found, we can say that, you know, we've got this function f of x. Well, we can also say that there's this other function which is exactly the same thing, f of x, plus any constant that we want. So we can come up with an infinite number of antiderivatives just by changing the constant. So let's take a look at an example here. We have a function f whose derivative is given to us, and we're also told that we're going to pass through this point 2, 1. Now remember, when we're trying to find derivatives or antiderivatives, we really don't like fractions. Fractions are great when we're finding maxes and mins, as we saw in a previous video. But here, when we're doing derivatives or antiderivatives, we don't like fractions. So the first thing I'm going to do is I'm going to take f prime of x, and I'm going to rewrite it as negative x to the negative 2. Now, I'm going to find my antiderivative. So to find my antiderivative, f of x, notice I'm not using the capital letter because I'm starting with f prime. So an antiderivative, remember, is one step earlier. So we only use the capital F when we start with the notation f of x. So here, if I start with f prime, my antiderivative is just lowercase f, normal function. So now what I'm going to do is I'm going to see if I can develop a rule for finding this antiderivative. Now, one thing we need to establish is that when we're doing an antiderivative involving powers, there's kind of a rule of thumb with how these powers work. So let's go back up to the original problems that we kind of worked out here, especially this number 4, and let's kind of look at what we did. So when we started with x cubed and we ended with x to the 4th over 4, The idea was this. We needed to realize that this 4 in my original function was going to get multiplied. And if it didn't exist over here in the derivative function, we needed to do some division to get rid of it. So essentially what we did was when we had a power function, x to the n, to get the antiderivative, if we're starting with x to the n, the antiderivative is just going to be the opposite steps. We're going to raise the power by 1, we're going to add 1, and then we're going to need to divide by n plus 1. So whatever the power was, we raise it by 1 and then divide by that new number. If there's any constants in there, then we would simplify. So for example, if we have 2x cubed, the antiderivative going backwards would be 2x to the 4th over 4. This way, when we do the derivative, which means multiply by n and reduce by 1, it's completely the opposite steps. When we do those derivatives, there it is on the screen, the 4 will have something to cancel out with. So similarly, just one more for good measure here, if we had 5x to the 7th, the antiderivative would be 5x to the 8th, raise it by 1, and then divide by 8. So this is the backward step from finding the derivative. So this way, when I find the derivative again, remember I'm going to multiply by 8, reduce it by 1, and then divide. This gets me back to the original derivative. So remember, this is my function, this is my derivative. I'm going backwards with these antiderivatives. So let's go ahead and try a few more examples here and see if we can get this down. So now we're going to use that rule that we just established where we're going to raise the exponent by 1 and divide by the new exponent. So my potential function here would be negative x, and when we add 1, we get negative 1, and then we're going to divide by negative 1, right? So when I simplify this, it's positive x to the negative 1, or just 1 over x. And I can always check to make sure that I have my derivative right. Now, I'm not quite done because I need to realize that it's not just 1 over x, it's 1 over x plus some constant c that I need to account for. And now here's where the original function initial condition is going to come into play here. This tells me that f of 2 equals 1. When I plug 2 in for x, I get 1 back. So essentially what I'm going to do is I'll come down here and I'll say, well, f of 2 is 1 over 2 plus c, and that's supposed to equal 1. Now I'm going to solve for c. When I subtract 1/2, I get c equals 1/2. So now my job is to write my final answer, and my final answer will look like this. F of x equals 1 over x plus c, which is 1/2. So I have to use that c, I have to put it back in for the constant. Using the initial condition is the only way I can solve for c. If I'm not given an initial condition, then I need to represent the existence of a possible constant with a plus c and just leave it like that. And we'll see some of those along the way. But let's kind of finish with one little example here. We'll be getting to the antiderivatives where we have to use the plus c later on. For now, our goal is to just get a handle on how they work, what they are, and how to find them. So example 2 says find the velocity and the position functions if the acceleration is 9.8. So acceleration is 9.8 and the body falls from a rest. So that's a really important piece of information because it's telling me that my initial velocity is 0. I can also glean from this that because I'm falling from a rest, my initial position, because I'm being dropped, I can also assume is 0 because at 0 seconds it's fallen 0 meters. So I know my initial position and I know my initial velocity. So now I'm going to remember that acceleration is the derivative of velocity. It's the second derivative of the position. So I need to remember this relationship here with my acceleration and my velocity. So now that I've kind of established that derivative relationship, now I can go ahead and find all my antiderivatives. So to find my velocity, I'm going to do my antiderivative of acceleration. If my acceleration is a constant, it had to come from some function where I had 9.8t. But then I also need to consider some sort of constant, right? So I know that my initial velocity, v of 0 will look like this, 9.8 times 0 plus 0, right? Or plus c. And I also know that my initial velocity was 0. So when I go to solve for my constant, 0 plus c equals 0. Lucky me, my constant is just 0. So my velocity function is just 9.8t. Now I need to find my position function. Now my position function is the antiderivative of velocity. So I'm going to start with that 9.8t, and my position function will be 9.8t squared. I raise the exponent by 1 and then divide by the new exponent, plus some constant c, which we're going to figure out, right? So s of t, s of 0 is, and let's see, 9.8 divided by 2 is 4.9. So 4.9 times 0 squared plus c, and that also equals 0. Lucky me, both constants are 0. That's not always the case. So my two functions that I had to find were position and velocity. So my position function is just 9.8, sorry, let's go ahead and use 4.9. 4.9 t squared, and my velocity was 9.8 t squared. Now, the point that I want you to remember here as you move forward and as you practice a few things with antiderivatives is that there are an infinite number of antiderivatives and they all differ by a constant c. If you have some initial conditions, you can find what c is. If you don't know what c is and you're not provided any initial conditions, then you need to represent its existence by just saying plus c. Okay? So, I hope this has been helpful for you, and remember, the best way to get good at this stuff is to just keep practicing. And so the more homework that you do, the more independent practice you do, the more mistakes you make, and then ask about those mistakes, the better you're going to be. So keep at it, keep practicing, and as always, you've got this.